A bidirectional scattering distribution function, or BSDF, is a mathematical way to describe how light interacts with certain material properties on an object. These are used in 3D rendering tools such as Blender to create physically accurate lighting in a scene. Tweaking these properties allows us to control how the material behaves in the final render, and this process is called forward rendering. In this video, we propose a pipeline that does the inverse. That is, given a 3D model and some reference images, how can we extract the material properties of a real-life object? The goal of inverse rendering is to estimate the parameters of a scene from one or more real or synthetic images. Because an image only represents the appearance or radiance of a scene, it doesn't have any underlying information about the scene itself, the meshes, materials, etc. In general, it is rarely possible to accurately reconstruct a scene's geometry, material properties, and illumination. The problem is inherently under-constrained, and there are many potentially valid solutions. In order to constrain the solution set, we photograph 3D printed shapes with known geometry, estimating only the camera position, material parameters, and the environment map. This simplification allows us to use a differentiable rendering optimization pipeline built using Mitsuba 3 to find a potentially valid representation of the real-life scene.
The initial stage of the pipeline estimates the pose of the object in the reference images. To do this, we first take the 3D model and render a bunch of random silhouettes. These are called templates. We want to find the template that has the closest per pixel match to the reference image. But notice that some templates differ from the reference only by a rotation, translation, or scale. To account for these transformations, we need to adjust each template to align with the image. We compute a transformation based on the centers of mass of the silhouette and its outline, using the angle of the line between these points to establish the object's orientation. We then apply this transformation to the camera and render the template again. Now when we compare the templates to the reference image, we get a more accurate measure of similarity. Finally, to get the best estimate for the object's pose, we iteratively update the camera using a differentiable rendering optimization loop in Mitsuba.
With the camera positions, we can begin optimizing for the rest of the scene. Our pipeline uses a modular staging system in which we optimize for different parameters of our scene during different iterations of the optimization. For example, in our first stage, we might only optimize the environment map, and in the second, we might introduce new parameters such as material color, roughness, and metallicness. This continues until we optimize all of our desired parameters in the scene. This is done to help mitigate the inherent ambiguity in our scene. For example, an object that appears yellow in an image may in fact only reflect yellow light from the environment. Since we do not know the lighting conditions, it is difficult to separate the lighting environment from the object's reflectance, and so limiting what we're optimizing for at any given step can help further constrain our solution. After the optimization loop is finished, we're given a dictionary of material properties we can import into any 3D rendering program.
Running the pipeline with synthetic input images gives results that closely match the ground truth material. With real-life images of 3D printed objects, our pipeline gives convincing results in many cases, even with a small number of reference images. There are three main limitations of our method. The first is that we only estimate a single material for the entire scene, so we can't capture objects with varying surfaces. Estimating a 2D texture for each object would make it harder to distinguish between the lighting environment and the reflectance. The second limitation is that we can't estimate anisotropic material parameters. While this isn't a problem for many surfaces, the 3D printed objects we use happen to be very anisotropic due to the layer lines created during printing. The third limitation is that we make assumptions about the camera's focal length and principal point offset, rather than estimating them in the pipeline. Doing so is possible, but adds complexity. Overall, our work shows promising results when estimating the material parameters of real-life images. Most of our pipeline's limitations have potential solutions, suggesting that this work can be meaningfully extended to a useful and robust inverse rendering tool.